extreme value theorem one of the value theorems, we talked about also an intermediate value theorem. This is another value theorem called the EVT. And the extreme value theorem states the following thing. Extreme value theorem. If f is continuous on a closed interval a to b, then f has both a minimum and maximum on the interval. Interval. So this is the extreme value theorem. Oh, weird bracket there, it's parentheses. The extreme value theorem, EVT. If f is continuous, note here this important condition. If f is continuous, this is a condition, must be true, meaning if the graph is like this, that's okay. If the graph is like with a hole and a jump, not okay. Must be continuous, right? Because if you have a broken function, you got a bunch of weird, breaks a bunch of rules. So smooth continuous curve, fine. Broken, not discontinuity, not okay. Or infinite discontinuity, whatever, any kind of discontinuity, not okay. If f is continuous on a closed interval, then f has both a minimum and a maximum on the interval. I mean, that's sort of makes sense. Just an obvious thing that we state called the extreme value theorem. So we're going to find those maximums and minimums by doing some examples. Find the max and min of, find the extrema, extrema of the following function. F of x equals 3x to the 4th power minus 4x to the 3rd power on the interval -1 to 2. Find the extrema right there. This in red here says, let me just try to write it better. It says condition. It's a condition. Condition, I-O-N. Condition. And it must be true. Must be true. Must be true. Must be true. Condition. Oh goodness. Condition must be true. So that, it must be continuous is what it says. Right? This is a requirement of this extreme value theorem. If your function is not continuous, you say, I can't do it, function is not continuous, and you're done. As long as the function is continuous, you're okay. But if the function is not continuous, you state, well, this function has a discontinuity on my interval, and so I'm not allowed to do that. So we're going to try it for this function. This equation here on the interval from -1 to 2. We're going to look at this function. We're going to try to find its extrema. Well, then that would be too easy, probably. So why would I do that? Let's find this extrema here. I think it's easier if it works. Sometimes it's easier if it works. So here we are with this equation here. I want to find the extrema. So the steps here, what we really want to do are steps. First, check your function. Check that f of x is continuous. Goodness gracious. Continuous on the interval. And there's no real formal way to do that. It's just a brief examination. This is a polynomial equation. There's no weirdness going on, so we can just breeze through that one. Yeah, check. That's fine. No problem. Done. If there was some derivative, if there was some function on the bottom, if it was divided by something on an x on the bottom on the denominator, right? That is a way we can get a discontinuity if we have a variable on the denominator, or if we have some kind of square root situation, right? A fraction exponent, some kind of radical. Those kind of things might cause some discontinuities, or an absolute value equation. Absolute value equations. Well, no, I guess it's not a discontinuity, or piecewise functions. Let's say piecewise functions, right? If there's some uncertainty about the continuous nature of your function, you have to check it out. But there's no uncertainty here. Here, this is very easy, clear, check, no problem. So we don't need to worry too much about it. Yeah, all that. ln, yeah, ln has a discontinuity, exactly, right? Logs have discontinuities. Exponential equations have horizontal discontinuities. That's okay. We're talking about vertical discontinuities. Yeah, all that discontinuity stuff, right? Remember all that from the limits way back then. Still bouncing around there, still bouncing around. You got to remember all that. So here we're good. This is fine. Breeze through that, check, no problem. Next thing we're going to do is we want to find the critical values. Critical values. And the critical values, those are the ones where the derivative equals 0 or the derivative is not existing. Those critical spots, those extrema, where the derivative doesn't equal 0 or does not exist. You want to find those critical values. Yeah, tangent's got a bunch of discontinuities on it. Secant and cosecant also got a bunch of discontinuities. I don't think we'll worry too much about that, but we'll look at some of these equations. All right, so to find these critical values, we're going to take a derivative. So we're going to ddx this equation. Oh, back to ddx. Thank God. No more ddt's, just regular derivatives. So f prime is equal to derivative of this. Look at this easy derivative. Look at these easy derivatives. Power rule, no problem. 3 times 4, that's 12. X to the third power minus 3 times 4, again, 12. X to the second power. Wonderful. So nice. Got my derivative. And to find my extrema, to find my critical values, I set this derivative equal to 0 and solve. I need to now know where are my variables, what x values will cause this derivative to be equal to 0. I need to set my equation equal to 0 and solve. All right, everybody brush off those algebra skills. How do I solve this? 0 is going to work, yeah, but why? What do I do? How do I get the x by itself, right? What do I do to here? Brush off those algebra skills. X equals 0 is definitely going to be 1. X equals 0. There's another one, though. And 1. Okay, good. Yes, x equals 1. Any others? How can we be sure these are the only ones? Let's go through the process and solve it, right? Brush off those algebra skills. How do I solve this? So what we did, all right, we're making up some answers. But what we did, we found the derivative, right? And we're looking up answers. We're trying to figure out an answer to what will be equal to 0 here. If I have 12x cubed minus 12x squared, what numbers for x would make this 0? Price is just kind of guessing numbers, but we want to make sure we can figure them out. So let's ignore these right now and see if he's right and what other answers there might be. How do we solve this? What process do I minus? Do I add 12x squared to both sides? Do I do some like what's my process here? Well, remember it's a cubic equation. It's some I got x cubed. Yeah, I got to factor out exactly. I'm going to factor out the 12 and the x squared. So I'm going to factor out 12x squared. 12x squared. Factor that out. And then I'm going to get, this is going to be x minus 1 equals 0. Why is this not? Excuse me. Okay, there you go. So factor out this 12x squared, right? We're doing some factoring, right? Brushing off our algebra skills. Then we see we have a 0 product property. Let me maybe not do this in red. Excuse me. Then we have our 0 product property, right? Where we have our split answers, right? This part by itself, 12x squared equals 0. And this part by itself, x minus 1 equals 0. And then, of course, our answers are x equals 0 and x equals 1. These are my two critical values. Critical values. Some quick back of the envelope calculations, right? So I got x equals 0, x equals 1. Third step we need to take. Once we have these values, check. Whoa, God. What's going on here? Check that your critical values are in the interval. Exclamation points on that. You may find a whole lot of potential or solved critical values. You may have 3 or 4 or 5 critical values in your situation. But the only critical values you care about are the ones between -1 and 2, the ones in your interval. The only critical values you care about are the ones between your interval. So, are both of these in our interval? Yeah, that's fine. 0 is between -1 and 2, yeah, and 1 also, that's fine. It's within the boundaries. So we're good for both. Check, 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 both between 0 and 1. -1 and 2, I mean, both -1 and 2. So we're good with that. We found our critical values. We found our potential maxes and mins, right? This is like one of these is maybe a max, one is a min, or maybe both are mins. I don't know. Our last step, whoopsies, our last step, we are going to check the critical values, check the critical values, CVs, critical values, and the endpoints and end points to find the max and min. You need to also check your endpoints, right? Because sometimes, like we said, the max might be like a little small local max, and the endpoint goes way up higher. So you need to check their critical values and endpoints for the maximum. And you do this by plugging in to f of x. You plug them all into f of x, find your max and min, find your values. And the way you organize this, organize in a chart. Organized chart. So you have x equals -1, your endpoint, x equals 2, your other endpoint. You have a critical value of x equals 0. So this is the left end. Left end, your right end. You got your critical value 1 and another critical value here. And then you plug them in to f of x. So you're going to plug in f of -1, f of 0, f1, and f of 2 in your original f function up here. Take all these, like the 2 endpoints, and then all the critical values you found in the middle, plug them all in to see which one's the highest, which one's the lowest. Let me erase this here and make a little more room here. It's helpful to have a little organized chart for you so you can see a little clearer what's happening. So you find your extrema, find your endpoints, find your critical values, and you plug into your original f of x equation the one that you're looking for, right? You're looking at this equation here. You're looking for the extrema of your f function, right? Where the f gets high and low. So you take this function here, 3x to the 4th minus 4x cubed. Let's write it down here. 3x to the 4th minus 4x cubed, your f of x equation. And that's a 4x cubed. And you plug them in. 4x cubed. So if I plug in a -1, I'm going to get 3 times -1 to the 4th power minus 4 times -1 cubed. Let's see. -1 to the 4th is 1, so that'll be a 3. -1 cubed is -1 times -4, that'll be +4. So it'll be 7 there. 0, I'll plug in the 0, that's just going to be 0. So that's 0. Right? That'll be 0. 3 times 0, 3 times 0, minus 4 times 0, that's just 0. Plug in a 1. 3 times 1 to the 4th minus 4 times 1 to the 3rd power. That's just 3 times, that'll be -1. If I do a 2, 3 times 2 to the 4th minus 4 times 2 to the 3rd. Let's see, 2 to the 4th is 16. 16 times 3. 16 times 3 is 48. 48 minus, let's see, 2 cubed is 8. 8 times 4. 8 times 4 is 32. So minus 32. 48 minus 32 would be 16, right? Minus 32. 16. All right. So we have our values, and we find our absolute maximum here. Here's our maximum. And this critical value right here is our minimum. And these are guaranteed points. I don't even know what the graph looks like, right? We have not drawn the graph, but I can guarantee that on this interval from -1 to 2, the lowest point on the whole graph is -1. Nothing is going to go below -1. Nothing is going to go below -1. And nothing on the whole graph, there will be 0 points, which will go higher than 16 on the right side end. Right? So that's guaranteed from this whole situation. Any questions about this situation? Again, we had our will they always be in that order, the maximum? What do you I don't know what you mean, like order. I mean, we found this one was the max. It happened to be this one is the maximum, and it happened to be this one's the minimum. But like in another equation, this could be the minimum and this could be the maximum. I mean, like it really doesn't matter. There's no like the last one's always going to be the biggest one. You know, there's no order. It's just you find all the potential spots, you find the potential places, and then you plug them all in, and you see, well, which one, where do they all fall? Where do they all fall? If you want to look at the graph of this, the function, the graph here, let's look at the graph here. I can just show you quickly what the graph looks like. Here we are from -2 to 1. The graph will look something like, it's going to have a, oh, and then the 2 here, this is -1, -1, -1 to 2. It's going to have a special spot at 0, a special spot at 1, and a special spot at 2. So it starts from here at 7. We know it goes to 0 at 0. It goes to -1 at 1. And it goes up to 16 at 2. So the graph is going to look something like, right, it's going to go down, flatten here, go down, minimum there, come back up. That's what my graph looks like. Something along these lines. And I know this, it's guaranteed to be this kind of way. It's not going to go suddenly down more down here. It's not going to go up over here. It's guaranteed to be curving down to flat here, minimum here, maximum here. This is the shape of this curve, sort of like guaranteed by figuring out these values of my function. All right. So this is some analysis we can do of functions based on what we know. So let's try one more time. Another way to find some max and mins on a chart from a function. Example, find the extrema of, here's a function, f of x is equal to 2x minus 3 x to the 2/3 power on the interval -1 to 3. On the interval -1 to 3. So are we going to have any problems with this situation? We have this fraction exponent. So the first thing we got to check are we going to have any weird discontinuities? Right? It's not a piecewise function, so we don't need to worry about that. It's not got a fraction. It's not got a denominator of a variable. There's no variable denominator. This is just a radical equation, a radical here. But sometimes radicals have a problem with negatives. Sometimes radicals have a problem with negatives, right? So maybe negative is going to give us a problem with this radical. Cube root of -1. Can I do that? Am I allowed to put this negative in here? This one, it's all okay. So the way, I guess, how do I, what hint can I give you? Odd roots can be negative, can be negative. So if you have like a cube root or a fifth root, you can do the cube root of a negative. That's fine. Like the cube root of -1 is fine. But even roots cannot. Square root of -1, not allowed. Or the fourth root of -1, not allowed, right? So it's a cube root, it's this radical here, which is like the same, remember this is the same as -1 to the 1/3 power, right? Our radicals are fraction exponents. This is like -1 to the 1/2 power, or -1 to the 1/4 power. Those are not allowed. Even on the bottom cannot be negative. Odd on the bottom, this cube root on the bottom, negative, no problem. Negative, no problem. All these little rules to remember. I mean, they make sense if you think about it, right? You can have a negative cube, but if you do -1, multiply it 3 times, you get back a -1. So the cube root of -1 is -1. Like the odd ones, they get back to negative. Evens, there's no way to get a negative from an even, right? That's where we get the imaginary numbers, right? That's where the imaginary number comes from. So the even ones are a problem. Odd ones are okay. So we're good here with our continuity. Everything's fine. So then our next step is just do the derivative, d dx. So f prime is going to equal, well, the derivative of 2x is just 2. The derivative of 3x to the 2/3, I bring the 2/3 down in front, so it's going to be -3 times 2/3. X to the power of, I do 2/3 minus 1. 2/3 minus 1 is -1/3. Right? I have 1 whole minus 2/3 of it, except it's 2/3 minus 1, so it's more I'm subtracting the 1. I'm taking too much away, so I got to have a -1/3 to make it up. So if I simplify this, 2 minus 3 times 2/3, well, the 3's here are going to cancel. This 3 is going to cancel this 3. So I'm going to be left with 2 here. And my x becomes on the bottom, because it's the negative x to the 1/3 on the bottom. So I've got to figure out now where this equals 0. So where does this equal 0? And this was a little more complicated to solve, right? Got a little more brush off our algebra skills. Let's think about how we're going to do this. I've got this equation here. I want to solve for x. So, well, I mean, easy thing to do, move this whole 2 over x to the 1/3 to the other side. Right? Add it to both sides, and just move this over here, right? Move this 2 over x to the 1/3 on both sides. Add it over here. So I'm going to get 2 equals 2 over x to the 1/3. And now there's sort of 2 things I can do. one thing I could maybe like, I don't know, this x, if I multiply x on both sides and then divide by the 2, right? If I take this x here, multiply it on both sides, get it to the top on this side, and then this 2 I divide, move it to the bottom on this side. One thing I can do is, if I do that, I'm going to get x to the 1/3 power equals 2 over 2. Well, really, okay, if I do this, I'm going to get 2x to the 1/3 power equals 2, and then divide by the 2 on both sides. So I'm going to get really x to the 1/3 equals 1, which is just x equals 1. If I cube both sides, right? How do I cancel the cube root? Cube both sides. Power of 3 on both sides. That's how I get rid of my fraction here. 1 cubed is 1 though, so that's fine. So that's one thing I'm allowed to do if I were to multiply x to the 1/3 on both sides. That's one option. So that's a potential answer. That's one of my critical values, x equals 1. Another critical value here. Another critical value, and another option I have to take. What's my other critical value? What other situation do I have in this problem that I have to deal with? If I multiply the x on 1/3 on both sides, that's great. I would cancel the x on the denominator. But I have an x on the denominator, everybody. I have a variable in my denominator. And so it's really nice if I cancel it and multiply it, but I have to deal with it. I have to deal with the fact that it's on the denominator. And whenever I have a variable in the denominator, I need to be aware that, well, something is a problem. I'm going to have to like pay attention. I'm going to have to what's the word I'm thinking of? I'm going to have to set a condition, right, where this denominator is equal to 0. I have x, let me do this in green, x on denominator, x in denominator, denominator means x to the 1/3 power is not allowed to be 0. So x cannot be 0. This is another critical value where f prime does not exist. This is a critical value it's not allowed to be 0, and so that's one of my situations where if I made my x equal to 0, my derivative would not exist. And so that's another critical value in my function. So these two spots, 0 and 1, are both critical values. And the 0 is a critical value because the denominator had a variable, and the denominator cannot be 0. So I've got my two critical values, 0 and 1. I want to check that those critical values are in my range. Yep, that's fine. -1 to 3. 0 is in that range. 1 is in that range. We're good. And now, once we have our critical, set up our chart. Set up our chart. We have our left endpoint, x equals -1. We have our critical value of 0. We have our critical value of 1. And we have our right endpoint of 3. Left and the right. Critical value here and critical value here. It does not matter that this critical value did not exist for the derivative, because I'm taking this critical value of 1 and plugging it into the original function. And that's fine. I'm going to get a value in the original function. Even though my derivative was not allowed to be 0, that just told me that that was something special. And that something special I need to deal with in the original function. So I plug them into f of x. Take my f of x, was my f of x up here. 2x minus 3x to the 2/3. So it was 2x minus 3x to the 2/3. That was f of x. So if I plug these in -1, let's see if I get -1. Let's do this like this. I've got 2 times -1 minus 3 times -1 to the 2/3 power. -1 to the 2/3 power is 1. -1 times 2 is -2. That's going to be plus 3. That's going to be a 1. 0, well, that's going to be a 0. 2 times 0 minus 3 times 0 to the 2/3. It doesn't matter, that's all 0. For a 1, 2 times 1 minus 3 times 1 to the 2/3. That's going to be a 2 minus 3. That's going to be -1. For 3, let's see. 2 times 3 minus 3 times 3 to the 2/3 power. I don't really know what 3 to the 2/3 power is. It's going to be cube root of 9. That's going to be ugly. 6 minus some crazy decimal. Use a calculator. I don't really mind. 3 times 3 to the 2/3 power. Something ugly here. To the power of, stop it, to the power of 2/3. It's like 6.24. 6.24, which is going to be -0.24. So it looks like we have our max and min. Here's our max. And -1, here's our min. Right? Oh, wait. Whoops, I did that wrong. My apologies, everybody. There's a question here. So if we get a derivative does not exist, can we still plug it in? The critical value is automatically 0 even if x can't be 0. Yes, the critical value is 0 because that's what we, right, that's the number that we're not allowed to do. That's the critical number. That's the number that breaks it. And so that's where we have to do this. How did I get 2x to the, it was 2x to the -1/3. So let me go back to my derivative here. With my derivative, again, I know we're out of time, everybody. Took the 2/3, multiply in front, right? 3 times 2/3. 2/3 minus 1 is -1/3. And that's how where my derivative came from. -1/3 becomes 1/3 on the bottom of a fraction. And that's why we had that critical value of 0. The problem I had here is this should be -3. Oopsies. -3 still. So this should be -5. And that should be our minimum here. Here's our minimum. And the 0, this one here, is our maximum. No, right, yeah, when we plug it here, when we plug it in, it's our regular equation. Here, when we plug it in to the function, we plug in the values. Which way are you talking about? Here? Here? This thing here? This thing here? When it's on the bottom, it doesn't need to be negative. It doesn't have the negative on the x equals 1. Here? Oh, here, yeah, that x to the 1/3. This here, I multiplied both sides to move it to the top of the fraction, and then divided by 2 and got a 1. Yeah, because I multiplied it. That's why it's on the top now. multiplied both sides by it. I didn't just move it up, I multiplied. I mean, I guess, 6 of 1 doesn't really matter. Negative 1/3 is also 1. I see. All right. Very good. All right, so that's your min, that's your max in this situation here. I want you to try some of these, everybody. I want you to try some of these, your homework, to be turned in when I see you again on, gosh, I'm probably not going to see you till Wednesday. Try this out, section 3.1 in the textbook, page 171. I would like you to try numbers 17 through 31 odd, and there's a bonus if you want to try 33, 37, and 39. (17 to 31 odd) and a bonus for those other questions. Give those a try. Find those maxes and mins. Do your chart. We will go over this on Wednesday when I see you next. You know what? We should probably have a study session, sometime before then. What about Tuesday? Tuesday study session? Oh, I see you again on Tuesday. That's right. Never mind, Tuesday. Well, that's fine then. I'll see you Tuesday. I was thinking this was second period. Well, then let's do Tuesday. No problem. If you have a question, let me know. In Remind, send me a question. Remind, I'll be happy to help you out. But that's it, everybody. Thank you very much. In the chat, type goodbye. Once you type goodbye, you're free to go. I will see you all next time. Have a great weekend. Bye for now.